Perfect.
Okay. Yeah.
All right, let me start the broadcast.
Hello from Golden, Colorado, and Utrecht in the Netherlands. Welcome to the CUAHSI Fall Cyberseminar series. I'm Reed Maxwell at the Colorado School of Mines, and I'm kind of the host and organizer of this series, where we're going to be talking about recent developments in continental to global hydrologic modeling. We have 4 really terrific invited speakers. Really excited. The lineup that we have, I think, is really amazing. And today it's my pleasure to start things off and introduce Marc Bierkens. Marc holds the Earth Science Hydrology Chair in the Department of Physical Geography at Utrecht University. And he's had a number of roles at Utrecht, including being department chair for physical geography for more than 5 years. He has done research and published widely on a range of topics and a range of scales, quite literally, from the plot scale all the way to global scale in hydrology, which really gives him a very unique perspective. He has a really wide range of high-profile publications. In fact, it seems like every time I turn around, there's another really interesting paper, including a paper that just came out in Nature that Marc's part of on climate change and effects on the Asian water towers. Marc is also has a number of awards, including being an AGU fellow, and is an incredibly distinguished career with numerous former PhD students that are in all facets of the research and education endeavor all over the world, and something just close to 200 publications and journal articles. Marc is also an editor of Water Resources Research, and is really, we're really lucky that he is going to share his perspective on global hydrology and water resources, review, trends, and directions. And so before I turn things over completely to Marc, we're going to hold questions until the end of Marc's presentation, and then the mechanism is that you will send questions to me by the chat function online, and then I will read the questions off as they're received. So with that, it's my great pleasure to welcome Marc, and thank you very much.
Okay. Well, thank you very much. It's a great pleasure to be here and from Utrecht and speak to all of you about some work I've been doing for the 50th anniversary version of Water Resources Research. About 2 years back, I've added some stuff, some recent stuff, of course, but it's basically a review on global hydrological modeling since the early 1980s until now, and it actually starts with this paper that was published by Pete Eagleson in the Trends and Direction, which is another famous water resources research issue in 1986. I think I must have read most of the papers in that issue, and one of them was about the emergence of global scale hydrology. And in that paper, Eagleson actually came up with a number of observations. And one important one, and it seems to be regular thought these days, but at that time that was something that was a new thought, is that hydrology is basically an Earth system science, and that human impacts are surpassing the scale of a catchment, which means that land use change, climate change, of course, but also direct changes to the hydrological cycle, think about water abstractions, dam building, occurs at basin scale or up, and certainly have impacts larger than a catchment. So in order to be able to analyze these changes, we have to also be able to view hydrology from a global perspective, and that means that we need to have global hydrological models. And at that time, they were not really around that much, or they were, or only in rudimentary form. And he came up with a number of problems that had to do with climate change, but also large-scale agricultural change and biodiversity change due to land use issues, land use change issues. And of course, if we want to build such models that were not there at the time, we also need the data to feed these models. These data were also not available at the time, because this is basically when remote sensing started to, well, the first wave of remote sensing products started to appear, parameterizing these models was something that was viewed as very far-fetched. And at the same time, he called for educating the young hydrologists of that time, of which I was one at the time, in global hydrology and in the context of Earth system science. Now, this was the start of this talk, basically, because what I'm going to do is trying to see what happened since 1986 in the field of global hydrology. So it's a little bit of a history lesson in that sense. Then taking stock, where are we now? How far are we? How far are we from his vision? And what are the recent trends and developments that are there? And also, what are imminent challenges to basically take the next step? And what these next steps are eventually for the future and beyond is what I will conclude with. So I hope to spend about 45 minutes doing this, and then of course I'm eagerly awaiting your questions. So if we look at the development of global hydrology, really we can actually distinguish three traditional fields in which this development took place. Atmospheric science, hydrology and water resources, and vegetation and carbon and terrestrial carbon modeling. And really the first models came from atmospheric science, not hydrology. And that had to do with the fact that a lot of the models at that time, the land surface components of climate models basically prescribed either a totally wet soil or a totally dry soil, which led to all kinds of wet and dry biases over land. And the first one who tried to deal with that is actually way back. It's actually way before Pete Eagleson's paper. Published a paper in that's Manabi. Published a paper in Monthly Weather Review, where he used a very simple climate model, and he took care. He added actually the hydrology of the Earth's surface, and he showed by that, by including the hydrology, that he was able to much better simulate pressure and temperature fields over the eastern United States and part of the Atlantic. This model was really simple. It was what is now lovingly called the bucket model of Manabi, and it is basically a soil moisture store that is creating runoff whenever it's full, and he took a value of 15 centimeters of its storage, and then if it's larger than 12.5 centimeters, you have potential evapotranspiration. There's no reduction of atmospheric driven evaporation, and it's linear reduced to zero depending on how much smaller it is than this 12.5 centimeters. A simpler soil model cannot be thought of, but it already did the job for creating realistic, like I said, temperature and pressure patterns. Now from that on, it took actually another possibly more than 10 years almost for the first real complete land surface scheme to appear, and that was a paper by Deerdorf, who came up with a land surface scheme that had a vegetation layer in it and soil heat flux, some soil hydrology and canopy interception. And from that on, the first generation of land surface models appeared. These are the ones that one can think of, and they focused really on trying to model the soil, vegetation, atmosphere transfer as good as possible, and it really focused on what happened in the canopy and the vegetation, much more than what happened with the hydrology. So the hydrology in these first generation schemes was a little bit simple. Then about 10 years later, people started to realize that these schemes are a little bit simple hydrologically. Also, again, you see that soils were drying up too much in certain parts, leading to warm biases over continents. So a more sophisticated soil moisture scheme had to be incorporated, as well as maybe also trying to look at runoff and lateral transport of water. So the second generation of land surface models came about, and VIC actually is one of them, as you can see, but also TESSL, which I know, which is a part of the ECMWF, were a forecasting model. And some of them really solve multi-layer richness equation. Some of them really solve just a few buckets, but most of them try to incorporate what you call subgrid hydrological processes, meaning that if you have a 200 by 200 land surface pixel, and it has a certain soil moisture, average soil moisture, you have to account for the fact that certain parts of that particular pixel are already saturated, because those are the lower parts of the pixel, and they're evaporating. So that subgrid variability is very important to capture the, change of wet to dry conditions and the other way around. Then about 10 years later we see that most of those land surface, second generation land surface model developed into what I would then call land earth system models, which means they not only try to include the SWOT scheme and some soil hydrology, but also proper hydrology, as well as biogeochemistry and carbon. And also some of them even have runoff routing in them. So these are really part of land surface, not only land surface models, but earth system models. So that's more or less the development in the atmospheric part, and these developments were so successful, also the improvements were successful, and that had to do with the fact that in atmospheric science, from the get-go, at least from the first generation models on, people were engaged in these multi-model intercomparison projects, whereby flux tower data often were used, or certain parts, certain pixels that were heavily instrumented, to compare the, for instance, the turbulent fluxes, but also the surface temperatures, and compare the observed ones to a number of those schemes, and try to explain where the difference with the data came from each of those schemes, but also where the difference among those schemes came from. And these actually led then to these successive improvements of these schemes. Now, the goals of these were mostly model improvement, like I said, but they were also used actually when used. These MIPS were not used in a single pixel, but large scale, even globally, to assess for the first time the global terrestrial hydrological cycle in terms of energy and water. And a specific part of those MIPS were were geared towards feedback studies. What's the importance of the land surface for regional climate? Now, it's not all Hosanna, of course, when you think about those MIPS. There's a lot of critique on it, and it's actually partly justified, of course, because what happens if you develop your models together, you get entanglement between the models, you start to use the same principles, the same data. It means that if you do, for instance, a multi-model assessment, you cannot do proper probabilistic statistics on the ensemble of the models, because they are basically entangled. Also, which models participated in that particular in these comparisons is a little bit haphazard. It had to do with the capacity of the groups, the different groups, to be able to deliver that data at that time. And also, whenever, especially these schemes become more complicated, when you see differences appearing among them, it's actually quite difficult to pinpoint where these differences come from. So it's not all what it's meant to be, but it did a lot for improvement. Now, some examples of these MIPS. This is the Global Water Resources Assessment. This is the Global Soil Wetness Project, Phase 2. And you can see that in this case, people try to use multiple models to assess the global terrestrial water budget and energy budget, and also look at some specific components. And what's also interesting is that people trying to look at how annual and intra-annual change or variation, how they relate to each other, and also how the differences among the ensemble members, which is a measure of uncertainty, even though not nice and probabilistically defined, how it relates to interannual variability. A very successful and very famous paper came from this GLACE project, where they used 12 models, where they run it 2 times. One they run it with full soil moisture in it, and the other one with soil moisture climatology, and looking at the precipitation differences between the 2 runs for each model, and then taking the average of, and if this difference is large, then soil moisture has a big impact on the precipitation through soil moisture evaporation precipitation feedbacks. And Randy Koster's paper in Science, they showed that the hotspots of this coupling appear in certain parts on the, like the Sahel and also the central US, for instance. There have been some follow-ups on these experiments, but this is something that that was really had really a big impact on the field, this paper. Okay, let's move to another field where, albeit later, the development of global hydrology appeared. This was the hydrology and water resources community. It really started in the late 80s and 90s, where people like Marc and Peter Gleek were analyzing terrestrial freshwater resources and showing that actually there were shortages were appearing at certain parts because of overuse. And a little later, the first detailed global water assessments became available. These were mostly based on statistics. So they use statistics of water use, for instance, from Aquastat, which are reported statistics from countries. And they used hydrological observations to assess how much water, which they call blue water, which is surface water that is available, and a proxy for that is runoff. And they compare this runoff in cubic meters or cubic kilometers per year with the water use, and assessing hotspots of what they call water scarcity, where use is large compared to availability. Now later on, they wanted to have a little bit more granularity in these assessments, and also do projections into the future. So the first macro-scale hydrological models, or MHMs, came about, of which water gap is probably the first one, and WBM, water gap, by a German group led by John Alcamo, and then after that WBM, Charles Ferris-Marty's group, and MACPDM by Arnell. So these were the first 3 global hydrological models. The hydrology was quite simple still in there, not much subgrid stuff in there, really water accounting at the pixel scale, but they also accumulated the runoff. And one of the nice things about it, that they started to also include human water use. And this was first done by, in WaterGap, it was really inspired by what we call the integrated assessment models, like they make at YASA, or the image model they make in the Netherlands by PBL. These are these models that calculate the CO2 emission scenarios, and they also have the human impacts in there. And the way that it's modeled in these global hydrological models, the first generation, was really based on that. Now these are some products of that. Usually a lot of this stuff is not so much in papers, but it's in reports by UNEP and UNESCO and the World Water Assessment Program, the Global Water System Project, where they assess once in every year what the status is of the global water resources, both in terms of scarcity, which you see on the left. This is scarcity in the amount of water per capita available, but also in the different types of water use. One step further, this is from the Aqueduct Water Risk website of the World Resources Institute, where they calculated for regions. They calculate what they call the water stress index, which is basically demand over availability. And if it's larger than 0.4, you are in water stress, and if it's larger than 0.6 or 0.8, I should say, then it is the water stress is hampering economic development. Now, these global hydrological models got a new boost after 2010, where both WaterGap and also PCR Glob came about. WaterGap basically started to include at time steps, so not as a separate module, but as part of the integrated part of the hydrological system, the water use system. So they included water demand calculations for the different sectors, water abstraction from groundwater and surface water, return flows, and also then finally the water consumption. Well, we built our own hydrological model at that time, around that time, first publications by Rens van Beek and Yoshiwara on PCR Glob 2.0. Well, in that case, it was the first version of our model. PCR Glob came about. And also the Japanese people, Hanasaki and co-workers, they came up with their own model HO8 a little bit earlier, that also in an integrated sense try to include water demand. And the newest version of these type of models actually runs not at a half degree, where most of these traditional models run, but even at 10 by 10 kilometer or 5 arc-minute resolution. Now the next slide gives you, the next simulation shows you 30 years of simulation with our model at 5 arc-minutes or 10 by 10K at the equator, showing you both river discharge, soil saturation, and snow cover. And we're going to look at this increase of resolution a little bit later. Eventually, we think that we can start doing this at 1 by 1 kilometer or even 100 by 100 meters globally. But that's for later in this talk. Okay. The third line of models that developed was actually from the vegetation and carbon community. They started with a model which is called biome, which is actually a quasi-steady state model that tries to estimate what the dominant vegetation type or mix is at a certain pixel. This is usually was run at 1 degree, so small. Large pixels, so small spatial resolution, and biome was really driven by monthly average climatology. So it was quite simple, a very simple one soil bucket model, trying to and based on temperature and precipitation climatology, a certain vegetation type was there. Well, a big step came later on, 10 years later, when Sitch et al. Came up with what they call LPA. LPA stands for Lund, Potsdam, and Jena. These are the 3 cities where the universities were that contributed to this effort. And they really made a real dynamic vegetation model, which is sort of the blueprint of a lot of the dynamic vegetation and biogeochemistry modules in the current Earth system models that we have. And it has a simple plant physiology and stomatal response. It models also in a simplified manner carbon assimilation using Farquhar's equation mostly, transpiration and growth, has some biogeochemistry, sometimes even phosphate and nitrogen, and very simple soil hydrology. Now, like you ever see in a good marriage, there's always offspring coming, and these are 2 new tastes that developed. People went their own way. There's LPJ gas, that is more from the Lund group, that included more complex vegetation structure and also actually species distribution. So it's more, if you want to look at biodiversity issues, that's interesting. And then there's LPA ML, which was more further developed by the Potsdam group. And they have a more complete hydrology, including routing and reservoirs. And actually, the latest version even has a groundwater reservoir in it. So it really becomes a proper global hydrological model. But it also has agricultural crops in there, so you can work on food security issues. Okay, so this is just an example of work by Esther Biemans et al., where they used the GRAND database. They included in LPJ-ML, and from that they actually estimated what the amount of the contribution is of these reservoirs to the amount of irrigated water, and basically gives you the importance of the reservoirs in the different parts of the world. Now this is a sheet that shows you the many data sets that are out there. And remember that Pete Eagleson also said we needed the right data sets to be able to do this stuff. And this is just an overview. It's far from complete, but of the different data sets that people have collected from remote sensing data, but also just by collecting data from different sources, even digitizing reports and so on. For model parameterization, meteorological forcing, mostly from climate models, or satellite products combined with reanalysis products, but also data sets used for calibration and validation of the models. And without these data sets, obviously, nothing could have been done. So it's very important that people keep on working on these, because the models basically are as good as the data you put in there. Okay, let's look a little bit on latest developments also. One interesting development is that I showed you the different developments in the different sectors, and what you can see is that recently, a few years back, EasyMIP came about. EasyMIP contributed to the 5th assessment report actually, and the idea was to use models from different sectors in a multi-model intercomparison project and to assess effects of climate change. And this is the effect of climate change under climate scenario RCP 8.5, the differences in runoff. And if you have these multi-models, you can actually not only show where the dominant changes are, but how many of the models are actually giving a consistent direction. So you can actually see, for instance, that in the Mediterranean, you see a consistent decrease in runoff under this scenario, and all the models predict that. Whereas in some of the Arctic parts of Russia or the former Soviet Union, you see that you have an increase in runoff. So this is a really nice way of combining these models to look at consistent signals. Now this next sheet is what I could call a genealogy of global hydrological models. I'm not going into it. You can watch the paper, the 1995 paper, to see if your model is in there, or if I've forgotten something. But what you see, what basically strikes from this is that how much earlier the atmospheric community started to model the land surface at global scale than the global hydrological community. And that's basically if you don't count the bucket model of Manabi, there's more than almost close to 15 years in between before we hydrologists started to do something with it. So that's interesting to see. Okay. Now, if we look back at Eagleson, we actually see that most of the things that he projected that would happen actually occurred. You know, we see that global hydrology through 3 different strains of development has come a mature science, mature field of research. It is central to Earth system science, at least if you look at the land surface part of all the Earth system models. Hydrology is really central in it because it steers both the biogeochemistry as well as the water and energy exchange between the land surface and the ocean and the atmosphere. There are large numbers of data sets available, and we have lots of students lined up that can work with these models and develop on them. So I think in that sense he was right on target with his projections, and also what was called for was actually done. I'm not sure if it's because of this paper, but at least it was quite a visionary paper. But not all is well there, because there were some missed opportunities. And what you see is that you see hardly any connection with the catchment hydrology community. You have this PAP. We had this decade of PAP prediction in engaged basins, where people were looking at different new runoff generating processes, trying to understand which process was most important. The global hydrological community was hardly connected to that, and the same PAP community also did a lot of in trying to do model identification and model calibration using all kinds of sophisticated Markov chain Monte Carlo methods, and also regularization methods, and these were hardly used in the global hydrological community. So there's still a lot to do here. Okay, let's look quickly at some recent trends. Well, if you look at recent trends, you can actually distinguish between two things. You can distinguish between technological advances, of which I show a number of but also new fields of application of global hydrology. Starting with the technological advances, this is a very nice map by the group of Paul Bates, where they simulate using a diffuse wave hydrodynamics the inundation inundation extent of a certain return period over Africa. And there are actually three groups working on that right now. Global flooding. Like I said, that's the group of Paul Bates. There's also the Japanese group led by Dai Yamazaki and Taikan Oki, and then there is the group by Hessel Winsemius and Philip Ward that use our global hydrological model together with some overbank redistribution scheme. And you can see that this is really starting to develop. And if you want to really look at a cool tool, it's called Global Flood Risk Analyzer. You can actually see what the flood risk is for a certain return period, also on the climate change, based on these type of models. Another trend is the inclusion of groundwater. Groundwater seems to be important for certain areas where you have shallow groundwater tables, and during droughts, groundwater is able to keep on contributing by convergence of groundwater to evaporation, which means that if you don't include groundwater, you're not able to get the persistence of warm and dry spells. And this is the first global groundwater table map that was produced ever by Yin Fan et al. And that appeared in Science in 2013. And at the same time, they used a rather simple method where they had they actually calibrated the e-folding depth of permeability, the way that permeability decreases with depth, and they calibrated to many head data. And the numerical scheme to do this is a simple relaxation scheme. We also, Inge de Graaf, one of my PhD students, also worked on trying to couple a two-layer mod flow model to a PCR glob model. So if you look at the picture on the left, you see the groundwater part. The groundwater part actually is then, which is usually a leaky bucket type of parameterization, is then replaced by a full-fledged two-dimensional two-layer groundwater model that runs on the globe. With that, we can also estimate the global groundwater table. This is groundwater table depth at 10 by 10 kilometer globally. But more importantly, we can also start to do analysis on, for instance, the impact of groundwater abstractions, over abstraction actually, on groundwater depletion. And this is the amount of depleted groundwater in cubic kilometers for the different pixels of some of those heavily over exploited areas, like you see part of the Ogallala aquifer here, and also the Central Valley aquifer. And this is interesting because it allows you to say, basically actually estimate how deep the groundwater table will be, how it will develop into the future, how long it will take, or how long do you still have before it's basically too deep to get the groundwater out. Other recent trends, if you have this groundwater and this flooding, like you said here, and also the water demand and water withdrawal, you really can do the whole system modeling that is really akin to Earth system modeling, but then focused on terrestrial water stocks. And this is what we're trying to do right now, where we use our fully coupled version. So it's a two-way coupling now at time step. Full water demand, water use module, overbank flooding, and also evaporation and flow. And all the reservoirs are in there as well. They are consecutively added from 1950 on. You can actually then force this with 20th century land use change. Also with what is called the ERA 20C, which is a reanalysis product from ECMWF that tries to estimate basically past weather from 1900 to now, and also force it with, in this case, with Yoshiwara's estimates of water abstraction over the last century. And then you can do century scale runs. This I showed you the last 50 years here, where on the left you can actually see the total water storage globally, the anomalies at least, and also you can see actually surface water storage increasing due to dam building, and you see groundwater storage decreasing due to groundwater depletion. Well, this is still work in progress, of course, but anyway. Another interesting trend I would like to point out that is quite recent is parameterization, and what is called seamless parameterization between scales. This is a nice experiment that we did in the context of the hyper-resolution modeling group, where we modeled the Rhine catchment with 3 different models, showing all these models have a half degree, which is in the middle, a half degree version, and a 5 minutes version, which is on the left. What you can see is the evaporation fluxes of these models. Those are the 2 left rows, one at 5 arc minutes and the middle one at half degree. And if you then look, if you upscale the 5 arc minutes and to the half degree, and then you subtract the 2, you can actually see that for PCA Glob, WB, our model, and water gap, it's not consistent. So the fluxes are not conserved, which is a pity, of course, because you want to have a flux conserving parameterization across scales. MHM, which is Luis Samniego's model, uses a thing called MPR, which is multi-scale parameterization. And if we apply that, and that's the next one, if we apply that to PCA Glob, we can actually see, we're looking again at the difference map, that we can actually do a much better job. So we're actually seeing that this MPR is a very promising method to arrive at across-scale parameterizations that are flux conserving. Other type of technological advance that people are going to talk about, like certainly Stefan Collet in his next talk, are these so-called 3D fully integrated groundwater surface water models that connect 3D richness equation with 2D either shallow water equations or at least diffuse wave approximations. And they try to model the whole hydrological system from first principles. Basically, you have a slab of soil or a slab of a catchment, and you rain on it, and then the hydrology comes to life by itself. And basically, they started out with catchments, but they're moving on to continents, whereas we as a global hydrological community start to go more hyper-resolution. So we will cross each other's paths somewhere. And I think this is the future of global hydrology, to be honest. Of course, there's still a lot of computational challenges and parameterization challenges that have to be met. But this is really where we're going. And this is a very nice example of work by Reed, Maxwell, and Laura Condon, where they show you how intricate different patterns are of the groundwater table depth where you see the nice imprints of the hydrological system in it if you go to very fine resolution across big parts of the continental US. Okay, now let's move to some recent trends, new domains of application. I'll quickly go through it. You see now, for instance, that they apply global hydrological models to food security. In this case, it's the change in green and blue water due to socio-economic change, calculated by LPJ, so the change in green and blue water use. You can take it one step further and move from food to hydroeconomics. This is a number of scenarios. On the left you see what is called the virtual water content. That's the amount of water that is contained in crop production. So what they did is they have a global hydrological model and a crop yield model, or crop yield statistics. This gives you the amount of water in kilogram of a certain produce, and if you know what the trade is on the right, you see the trade links. You can also work out in socio-economic and climate scenarios that either yield a low yield or a high yield scenario, what the impact is on the current trade and also the pricing. And it's very interesting stuff. Another domain is energy. Very interesting stuff by Michelle van Vliet. It's used over US and Europe, as you used VIC in this case, together with a temperature model to estimate what climate change will do by decreasing runoff during the summer and in increase in water temperature on the water temperature, and also on the ability of electricity power plants to take in cooling water. And if they can't take it in, they basically have to reduce their capacity. And what you see here is the capacity reduction under a certain climate scenario, which is very interesting and very worthwhile exploring. This is very recently I added. This is health. It was not in the review paper. I actually forgot that part, but I should have been in. And this is recent work by some colleagues in Wageningen, Nienke Hofstra and a PhD student, that modeled the emission of cryptosporidium, which is a protozoa that causes a lot of diarrhea. And it actually shows you the current emission here in numbers on a log scale of those cysts per pixel. And then below you see that per country, but also how it will develop under a certain socio-economic scenario. And then finally, biodiversity. This is the paper by Charles Ferris-Matty with loads of different, really an interdisciplinary paper where they use a global hydrological model as a basis, as a backbone, to analyze changes not only in human water security, but also in all kinds of threats to biodiversity. And as you can see, the pictures are almost identical. There where water for humans becomes scarce, the human water use has the prerogative, obviously, and you see also that biodiversity is under threat. Finally, a new domain of application is what we call hydroclimate services, where you really try to online represent the results of those global hydrological models for the general public. These are just two of them that we worked on. For instance, the Princeton group has a very nice global drought forecasting tool. JRC has a European drought forecasting tool. ECMWF has a global flood forecasting tool, and so on. And these are just two examples that we made based on our global modeling results. Okay, now let's move to some imminent challenges that I think are still out there. And one is basically a long outstanding issue, is that if you look at the performance of the global hydrological models in terms of reproducing runoff or discharge, it's not really that good. I mean, in terms of correlation coefficient, it's okay, but if you look at Ness-Hut cliff, there's a lot of negative Ness-Hut cliffs. Not only our model, most of the models. It gets a little bit better if you go to the 5 minutes, but it's still quite poor, and to my opinion, a lot of that has to do with the poor accuracy of global gridded rainfall products. And also with the poor runoff representation in these global models. There's really lots of room for improvement still. And if we want to go one step further, if we want to be more accurate and also go higher resolution, we actually will not, it's not like in atmospheric science that you get the dynamics better at higher resolution, so it's only a computational issue and you get better results. Unfortunately, in hydrology, you also have to get the associated better data. And there are a number of data that are very difficult to come by that we really need. One is global river geometry and bathymetry. River diversions are becoming more and more important, and also local redistribution networks to see how much of the irrigation water comes from the pixel itself and how much comes from outside the pixel. And not last, but certainly not least, information about the subsoil. We really need better global hydrogeological data to have meaningful groundwater representations in our models. Now this is, I'm gonna only shortly pinpoint what we call hyper-resolution model. If we go to smaller and smaller scales or higher resolution, what you see that simple subgrid concept breakdown. What could be represented, for instance, moisture, soil moisture, what could be represented by a simple top model type of scheme, or a statistical downscaling procedure using only univariate distribution, really becomes a multivariate geospatial problem, and you really have to add additional information to be able to represent what happens at the smaller scale. And for that you need certainly additional data. And Keith Bevan and Hannah Cloak wrote two commentaries on our hyper-resolution work that were, of course, they were right that we really have a long way to go in getting additional better data for these global representations at higher resolution. If we don't have them, it doesn't make much sense. And then, of course, the computational challenges that are out there, but I think Stefan Collette in the next webinar will talk about that more extensively. Another imminent challenge, finally, is the human factor. I want to close almost with that. These are, it's a little bit of a busy figure, but it shows you for three different socio-economic changes. It's work by Yoshiwara and co-workers. What the different models for the different times, what the trends are in water use, in this case industrial water use. And you can see the trends are not, and the magnitudes are not only different between the models, but also the trends can actually be reversed. So we really don't understand what makes future human water demand tick. And if we want to include the human factor, we really have to understand how humans will respond to water stress in the future, and how they will respond to changing their crops, changing the technology, and so on. So what enters here is a new fashionable field called social hydrology, where they try to model these human water interactions with these stylized models that are actually very much like eco-hydrological models I've seen. And in my paper I also come up with this framework that shows you how basically water availability and water demand is modulated by the actors that actually have to make decisions about how they distribute the limited resource, the withdrawal, over the different sectors. And that decision they're making basically is influenced by physiographic constraints. Can you build dams or not? Do you have enough water or not? Economic constraints. Do you have money to do the investments or not? And also all kinds of cultural, legal, and institutional constraints. And that determines what policy and technological response is possible, and that feeds back into water availability and water demand. And this framework really calls for, I think, individual-based modeling approaches. So my last slide a little bit over time, about 5 minutes, sorry about that, is about how I see the future and beyond. I think it's a combination of those things. I think we're moving towards these global Earth system models that are totally physically based. And these Earth system models have coupled ice, terrestrial, atmosphere, and ocean in there, like like CESM already has. But the land surface, as it's now in there, which is now a CLM, is probably going to be represented more like models like Parflow or Hydrogeosphere, where hydrology basically is modeled more computationally by 3-day Richards equation and shallow water equations, and hydrology is more emergent. And that's added, and that's not so good, not so well represented yet in these models, with a water use modules. And this whole framework is then put into an integrated assessment modeling framework that drives these Earth system models in terms of demography and economy, land use change, available energy and resources, etc., etc. So we're moving basically to Earth system models, part of integrated assessment models, where hydrology is just one of the puzzles that we have to resolve at a global scale, at high resolution, with all the challenges that are out there. So that concludes my talk, and if there are any questions, I'm open. Thank you.
Okay, thank you very much, Marc. That was a really outstanding presentation and a terrific overview. So I have a couple of questions that have been chatted to me through the system. First, I'm going to make one quick comment. So there's been a number of people asking about whether or not this will be available offline. And CUAHSI is recording the entire webinar series, so the whole thing is available offline, and I'm sure there'll be information from CUAHSI about where that will be linked. So in terms of the questions, the first question, Marc, speaks to your model intercomparison and integrated models and other kinds of models and sort of what the future holds. And so this particular individual wants to hear your opinion about whether these models can or will be integrated into one model, or whether it'll still sort of stay in the intercomparison framework. What are your thoughts on that?
Yeah, I think it will be there will be multiple integrated models. That's what I think. Just like there's now multiple climate models and also multiple Earth system models. Hadley has one, right, and NOAA has one, and right. So I don't think it will converge to one single model. It will be multiple models, but there will be probably fewer of them, because once you start integrating these models, they basically, you can either go the community way, or you can throw a lot of money at it, like the EU tends to do, and have big institutes carry it. So small university players like us basically will work on components, but not on the model as a whole.
Great. Yeah, I tend to agree with your perspective there too. So the next question comes from Todd Rasmussen, and this is says, while there has been substantial investigation of relationships between atmospheric and hydrologic sciences, could you speak to the relationships between ocean sciences and hydrology, especially estuaries, continental shelves, influx of terrestrial contaminants, such as what happened in Fukushima, on oceanic processes?
Yeah, if you there are communities that basically look at the continental, say the shelf waters and terrestrial hydrology. There's the Global News Network that looks at the emission or the export of nutrients, mostly NMP, but also now microplastics and even emerging substances like oestrogen and so on. They're looking at those substances and how they end up in the coastal ecosystems. So people are working on that. There's not much connection to the global hydrological community and the ocean modelers, even though the ocean modelers do have a in their ocean models, if they are not slab models but they are dynamic, they do have fresh water forcing in there through a very simple accumulation scheme, and that looks a little bit like TRIP. So they basically do that themselves without the hydrologists. That's my understanding a little bit.
Great, thank you. So the next question, and thanks audience, you guys are being really amazing and lots of really great questions coming through. So the next question is, there's a large discrepancy between modeling and observational scales for small islands, many of which are already showing effects of climate change on their water resources. Can you comment on some of the tools or techniques available for resolving this discrepancy?
Yeah. I think that, to be honest, our global hydrological models are not very well suited to take up these islands yet. So we have to go to much higher resolution to be able to pick it up. I think if you want to analyze the problems with these islands, whether they're atolls or smaller barrier reef type of islands or volcanic islands, you basically, what I would do is, if you want to have a global perspective on that, is pick out a number of archetypal islands in different climate zones and then analyze these more in depth. Not try to do that with a global hydrological model. I don't think it's a suited tool yet to do that.
Great, thanks again for that answer. So I'm skipping around a little bit, but there's another really timely one, which basically comes from Steve Kramer and says, what role can satellite remote sensing play in informing global hydrologic models? For example, GRACE for groundwater storage. And of course, the timely part there is that it looks like GRACE has gone offline, but that's a whole topic for a different point. So can you comment on remote sensing and remote sensing products and how they can help inform or help to inform the global hydrologic models?
Yeah, I think there are three sets of models, or three sets of there's four ways by global hydrology can benefit from remote sensing. GRACE is one. It enables us at least to get the total water storage right, and a recent work by Bridget Scanlon shows that we still have far to go when it comes to the global hydrological models compared to GRACE, even though GRACE of course has its flaws as well, but anyway. But the other one is surface water routing, discharge by LiDAR or radar, and also the other one is soil moisture, and then finally evaporation. And I think that especially for these global flooding initiatives, radar and LiDAR to get flooded areas right is a very cool tool that will enable us to greatly improve the parameterizations. And I think the soil moisture is a little bit cumbersome, because soil moisture basically is only the first few centimeters, not profile soil moisture, and none of the land surface models really is able to model that well. So I tend to have more faith in these new set of evaporation products, because if we have PRESHIP, if that's okay, like GPM, we have good discharge measurements. Now we arguably that may be a problem, but at least we have GRDC and FRIEND and some of those data sets. Then if you have additionally you have evaporation, you actually constrain the whole model, because you have basically the fluxes at longer time scale, and if you want to go to shorter time scale, you add GRACE to it, and you have the complete picture of storage chains and inputs and outputs. And that will really, if you use that in unison, that will really help constrain these models. Up to now, they've been used in a data assimilation framework as a sort of statistical correction to estimate global threshold water budgets. But the next step is to use them to actually calibrate those models, or even improve the dynamics of those models. So I see a great future for that and lots of unexplored opportunities.
Great, thanks. So the next question is from Steve Burgess, and his question is specifically about including fires or other things like this, but I would extend it to land cover disturbance. So there's lots of forms of land cover disturbance: fire, deforestation, urbanization, just to name a few. And I'm curious about your comments about how these could be, or could be included in global hydrology.
Yeah, there is a lot of evidence that fire has a big impact on the runoff response of catchments, and also on the runoff the runoff coefficients of catchments. So that is certainly very interesting to include. But we haven't been doing it. I don't know of any other group who has been doing it. What I do know is that we have been, and also the LPJ people, we have been looking at land use change. And one of my postdocs has been looking at comparing 1850 land use change to current land, or the land use change since 1850 to now, and it has an evenly, if you take land use change, it has basically as large an impact on the global water resources as climate change over the 21st century. Of course, it's going to be climate change is going to be more important into the 21st century. But if you look at past change, land use change is as important as climate change, as well as in other changes like reservoir building and water extraction. So it's a very important component of understanding past hydrologic change, I think.
Great, thanks. So the next question comes from Ann Nolan, and Ann would like you to expand a little bit about the challenges of modeling snow at the global scale. And obviously, there's a lot of challenges, but snow is one of these. And if you could comment on progress there.
Yeah. Well, one of the things that helps when you start modeling snow, what I found is up to now in these global hydrological models, I'm not talking about land surface models that have an energy balance in them anyway, is that putting an energy balance in, we already know that from catchment studies, that because of the limited data to feed these energy balance models, any degree day method basically does as well. Unfortunately, that's still the case. What does help a lot is concentrating on basically resolving the topography better. That helps a lot. So it means that you have to either go to a finer resolution grids, that already helps, or like in VIC, for instance, and actually we had it in our old model, we still have to implement it in the new version, is to implement elevation zones. And then per elevation zone you have a tessellation of different land uses, and also a distribution of snow and non-snow covered parts, and that helps a lot if you do that. So it's more topography, I think, than energy, than more sophisticated energy balance models to get the snow correct. At least given the poor information that we have often on the different things you need for a full energy balance model.
Great, thanks. Okay, so I think we have time for one last question, and there's a number of questions that are similar. That'll be a nice way to sort of end your presentation, a really nice presentation, Marc. And this is really combining a few questions, but thinking about spatial scales. And so there have been a lot of questions about, can we scale our physical equations obtained from field scale studies like Richard's equation up, or can we borrow from more top-down approaches? And you made a really nice comment about these approaches, types of models meeting in the middle. And I wonder if you could talk a little bit more about scaling of the equations, scaling of the processes, and where you think this might end up.
Yeah, yeah, that's a tough one, I think. I've been struggling with that. I mean, the question one should ask actually is, because you see that a lot of those land surface models, they use Rich's equations at 1 degree. And then, you know, okay, I mean, they're not able to predict soil moisture at a point, but they get the fluxes correct. So somehow, but that's also the case for models that just use connected buckets, you know, with some mechanism that determines the emptying of the bucket based on soil moisture. So basically at the large scales, as long as you have something like a force restore type of mechanism with a negative feedback on that outgoing fluxes are proportional to the storage, then you can always get it correct if you have the fluxes observed. So so as long as you are only interested in the vertical exchange between the atmosphere and the land surface, I'm not sure if much more sophistication is needed. But it will be, of course, important if you think about things like groundwater recharge, and also, especially, I think, if you look at runoff generation mechanisms, and especially if you start looking at water quality issues, then it really all the macro pores become important, and you're not averaging that out anymore. You have to basically arrive at upscale distributions and equations that reproduce those distributions. And we may, I think we had this review paper with Martin Clark, where I think we may want to look at what people have been doing in stochastic subsurface hydrogeology, where they were able to get effective dispersivities from the, you know, the smaller scale models of the smaller scale distribution, and even derive macro scale equations. So that is, once we look at runoff generation, groundwater recharge, and quality modeling, we may have to go that way before we arrive at a scale in 20 years or 30 years from now that really is really 1 meter, and you can really start using Richard's equation again as it is. So that's how I look at it, I think.
Great. Well, Marc, thank you so much. Let's all give Marc a round of applause. You can only hear me applauding, but hopefully everybody is also applauding for that great presentation. This is just the first of 4. We have 3 other terrific talks lined up. Stefan Collette is talking same time next week. Then David Gotchis will be talking, and then Laura Condon will be talking. And so we've got a really nice lineup for you guys. I really appreciate all the great questions and all the attendees. I think we have more than 150 people attending online, which is really terrific. All right, so I'll turn it back over to Liz so she can wrap things up. But thank you very much, Marc.
Yes.
And thanks everybody for attending.
Really enjoyable. Thank you.
All right, everybody. Thank you very much for attending, and we will see you next week. Or
Okay.
hear you next week. All right. Bye, everybody.
Bye.